Well, let's work an example that includes the work energy theorem, utilizing also friction and spring potential energy and kinetic energy. And it's going to be a 5-kilogram monkey, very nasty creature, who definitely needs to be punished, as you can tell, just by looking at his facial expression. But we'll get to that momentarily, namely the corporal punishment aspect. So the spring is unstretched that he's hooked to, and you're going to give this monkey a shove in this direction, 2 meters per second. And the question is, how far does the monkey go to the right when sitting on frictionless ice, and then also with a coefficient of friction of 0.3? So the spring constant is 120 newtons per meter. So what is this distance? So let's do the free body force diagrams. And here's the point in question. And a free body diagram, we have mg, the weight of the monkey, we have the normal force, and we have the spring force acting on the monkey. With the case of friction added, we have mg, we have normal, we have spring force, and we have friction. So we're going to do both cases. Let's take a look at the case where there is no friction. So consider very carefully here the work by mass on spring versus work by spring on mass. So the work by mass on the spring is this monkey is given a shove. It does work on this spring. Keep in mind that the mass then is pulling on the spring to the right and it's moving to the right while the spring pulls backward. So what is the work by mass on spring? Well, the force by the mass is to the right, and it's moved to the right. Therefore, they're both going in the same direction, so we have 1/2 kd squared. D is x in this case, the stretch of the spring. The mass and the direction of force and the motion are both in the same direction. Okay, so now work by spring on mass. What work does the spring do on the mass? Well, as the mass goes to the right, the spring is pulling to the left. So since they're oppositely directed, it's minus 1/2 kd squared. Very important. So the spring is doing negative work. The mass is doing positive work. All right. And the work total on what? Well, on the mass. Total work done on an object is delta K. That's the work energy theorem. So let's apply this to the monkey. Final speed is 0 because he's going to be shoved at 2 meters per second, but then come to rest somewhere, well, here at the end of D. So we have the work done by the spring on the mass, 1/2 kd squared. So that work, that's the total work, and that's delta K. So delta K is final K, which is 0 because it comes to rest, minus initial kinetic energy. So you see these minuses go away, the halves go away, and we can easily solve for the distance from this. We'll do on the next slide. So then the distance is square root of mv0 squared over k, v0 square root of m over k. Plugging in the numbers, v0 is 2, m is 5, k is 120, and it's 41 centimeters. That's our answer. Let's include friction now. Here's the new free body we already looked at. So we add the friction. So work is going to be done by friction as well as the spring. Notice these forces are in the same direction. So both of those forces are going to manifest negative work on the monkey. But nevertheless, that total work produced by these two forces must be delta K. So work done by friction is minus friction force times distance. Work done by friction is usually negative. So that's friction force, mu k normal, which is mg times d. All right, so then work total is delta K. Let's go ahead and account for all of it. We have the work done by the spring, 1/2 kd squared. It's going to be a different d than before because we now also have work done by friction, minus mu k mg d equals final minus initial kinetic energy. Let's rearrange this. 1/2 kd squared plus mu k mg d minus 1/2 mv0 squared. You'll notice this has a quadratic form. And so let's go ahead and plug numbers in now. 60d squared plus 14.7d minus 10 is equal to 0. So you work out the quadratic solutions and you get minus 55 centimeters and 30 centimeters. So 30 is our result that we are looking for. Quite a bit less than 41. Finally, what's the minimum coefficient of friction to keep that very obnoxious monkey from sliding back? He slid 30 centimeters to the right. So the coefficient of static friction is that friction force divided by the normal. Friction force being Kx, normal force being mg. So that's 120 times 0.3, 5 times 9.8 is 1.35. Now that's a pretty high coefficient of friction. That would require a force of 1.3 times the weight to cause them to slide. So that's pretty sticky surface. So it's not all too likely that the coefficient of friction is going to be that high, which simply means that our obnoxious monkey is going to slide on this rough platform. And that should cause his little butt to get burned a little bit. And as I said before, he deserves to be punished. And so maybe this will be a little bit of justice due this obnoxious monkey. That's right. Take that, you little scoundrel bipedal primate. Not even really biped, half quadruped. That changed your expression a little bit, didn't it? Take a little spark out of you, you little varmint.